In our fourth and final video, we're going to look at analysis of variance and regression. Essentially, the question we're asking is the regression line a good fit? That is the question we're asking. Is the regression line a good fit? And we could test that alpha is 0.05, right? So if the regression line is not a good fit, the p-value would not be significant, and pretty much you would have a very low coefficient of determination, a very low R value, which is correlation coefficient. So we want to test that. The way we do it is actually by analyzing variation in regression. So let's break that down to see what that looks like. So the total variation regression, which is basically the variation in the values of y, is y minus y bar squared. If we add that all up, that is SSY, right? So SSY represents all the sum of squares due to y, which means it's capturing the variation among the y values, right? Well, it turns out that if we actually break that down, SSY is made up of two parts. It's made up of the sum of squares due to the regression, SSR, plus the sum of squares due to the error, SSE. So this part right here is actually y hat minus y bar squared. And whereas this part right here is y minus y hat squared. So that is the sum of the errors, squared errors, that's the formula, the sum of the squares due to regression. And then this one right here is y minus y bar squared. So that's the three parts that make up the variation in regression, all right? Now, this we already could find because we have the formula much early on for how we find SSY. We can find SSY simply by doing sum of y squared, sum of y all squared over n. That we already knew. Remember also too, I showed you how we could find SSE. SSE was SSY minus SSXY squared over SSX. All right? So that is SSE. Now, to find SSR is fairly easy, because if we know how to find SSE, then SSR is just SSY minus SSE. If you think about it, if this is SSY right here, the total sum of squares for regression, for the overall regression, and this is SSE, then this piece right here must be SSR. But we don't even need to calculate all three parts separately, because as long as we have two parts, we could find the third one. So here's our SSY right here. Here's our SSR in this block right here. And we can find SSE by simply subtracting SSR from SSY, right? So what we now need to know are the degrees of freedom, and then we could actually set up an ANOVA table. So let us go through a hypothesis test, and then I will actually show you the formulas that we need as we go through that. So the question is the regression a good fit? Test that alpha is equal to 5%. Is the regression a good fit? test at alpha 0.05. So HO, HA, the regression is not a good fit. Is not a good fit. Versus the regression is a good fit. All right. I don't have any symbols for that. That's basically how we express it. That's step 1, hypotheses. 2, test statistic. It's an F distribution, analysis of variance, and it is MSR, that's the mean squared due to regression, over MSE, the mean squared error. Sounds familiar? So MSR mean square regression and then MSE mean square error. All right. So how do we find MSR? So MSR will be SSR over K. K is the number of independent variables. K, number of independent that's K. All right, and then SSR, I showed you earlier, SSR is SSXY squared over SSX. Cool. Let's find MSE. Well, MSE is equal to, I'm giving you all the formulas right here, SSE over N minus K minus 1. That's the degrees of freedom right there. I should mention for the first one here, the degrees of freedom, numerator degrees of freedom was just K. Now this would be the denominator degrees of freedom, df2 will be N minus K minus 1. So notice K is 1 because we have just one independent variable. And so it becomes N minus 2. K minus N minus 1, N minus 2. All right? So that's the degrees of freedom right here. And the ratio of those two values gives us an F statistic. Cool. So that was the test statistic. Decision rule. This is a new page. So we know the F statistic is kind of like this. It's skewed. This will be alpha 0.05. So we have an F critical. F critical turns out to be the F alpha over 2. F alpha df1 df2. But what is alpha? 0.05. What is df1? Is equal to K, which is 1, and df2 is equal to N minus K minus 1, which is equal to N minus 1 minus 1, N minus 2. But what is N minus 2? N minus 2 for our problem is 8. 10 minus 2 equal to 8. So therefore our critical value is F 0.0518, which turns out to be 5.32. That's the critical value, 5.32 if you look up the F table. And So if our F observed is greater than or equal to 5.32, reject HO, or if the p-value is less than 0.05, reject HO. Cool? All right. So now let's find some of the values that we need. We're going to need SSY, which we already have. We're going to need SSE, which we calculated earlier. And then we're going to need SSR. So let me find those values. And we're going to work with that. SSE. Cool. So here we go. Step 4. Analysis. So we already know that SSY, okay, since we did that before, SSY is equal to 2258.1. We already had calculated that SSE from our earlier problem when we were doing the test for beta 1. We calculated that SSE was 917.66. 917.66. All right? So we're going to need to be able to calculate the difference between those two values to give us SSR. So let's put our values in an ANOVA table. Sources of variation. SS, degrees of freedom, MS. So the same principles, you notice. Then we find F critical, and P value. P value. I'm running out of space here. Sorry. So we will put the sources due to regression right here, the error, and then our total. Well, the total we know in terms of our total SS value is the 225.58.1. 2258.1. 2258.1. For the error, we know our value is 917.66. 917.66. 917.66. We know the degrees of freedom here is 1. The degrees of freedom here is 8, which gives us a total of 9, n minus 1. Now let's find the difference between 2258.1 minus 917.66. So that is 134044. 134044. All right. Let's bring this down a little bit. So the mean square, which is due to regression, is just 1340.44 divided by 1, which is 1340.44. The mean square due to error is 917.66 divided by 8. That's 917.66 divided by 8. Turns out to be 114.71. 114.71. Now let's find the F value, which is just equal to the ratio of those two values. Turns out that it is 11.685. 11.685. And remember, our critical value is 5.32. So if we're using the critical value approach, we'll just compare the 11.685 to 5.32. All right? But then now, if we want the p-value, we need to go to the F table. When we go to the F table, under 1 degree of freedom in the numerator, 8 degrees of freedom in the denominator, then what do we get? It turns out that the largest value that we have for F is 11.26. 11.26, all right? But we have 11.685. Now at 11.26, the area in the tail is 0.01, which means our p-value is less than 0.01. Now you notice something? You notice how this is consistent with what we did with the 2t test? Same p-value. Excuse me. We will actually have the same p-value for this question. So now that we have the F table, step 5 is all we need. Step 5, decision, conclusion. So since p-value is less than 0.05, reject the null hypothesis. What do we conclude? We have sufficient evidence the regression is a good fit. There is sufficient evidence that the regression is a good fit. When we say fit, what we're saying is that when we draw this graph, we had a bunch of points, that the regression line fitting through these points is a good fit. All right? And because right now it's capturing about almost 60% of the variation, our R value is 0.7705. That's pretty good. And in both cases, the 2t tests that we did for correlation and for the slope, they were both significant. This regression is also significant. So we have what we need. Since we rejected the null hypothesis, of course, then we have a risk of type 1 error. Risk of type 1 error. And that risk is less than 0.01. All right? So that brings us to the end of regression, because we will stop at analysis of variance. And so we now have full coverage, and you notice that we actually went through, we did point estimates, we did standard error, we did confidence intervals, predictions, and then analysis of variance. It's almost like we ran through every single thing that we've done in the course beforehand on this particular topic. All right? So analysis of variance, just to sum that up, essentially, if we want to answer the question, is the regression line a good fit? What we do is we analyze the variability in the data that we have, and then see to what extent that the regression actually captures most of that. Regression currently captures about 60%, 59 point something percent. And what we do is we break down the total variation, which is SSY, into two parts. Variation due to regression, variation due to the error, what we cannot explain. And of course, you want the variation due to the regression to be much larger than the variation due to the error. And so we find that the variation, we need SSR, and SSR can be obtained by subtracting SSE from SSY. So we have formulas. We have formulas for all three. We have the formula for SS of y, which we are used to in calculating the sum of squares for a single variable. And then we have the appropriate formula for SSR, which is SSXY squared over SSX. And if we subtract that from SSY, we get SSE. All right? Simple as that. The degrees of freedom associated with the regression is just the number of independent variables. There's only one in this case, so that was 1. And then degrees of freedom associated with the error is n minus k minus 1, which is n minus the number of independent variables minus 1. In this case, there's only 1, which gave us n minus 2. And then after that, of course, the degrees of freedom associated with y, the y values, just a sample of y values, would be n minus 1, just as if we were doing x values, or a sample of x values, same thing. So with that, we're able to set up an ANOVA table, and that ANOVA table showed us that we had a very large 11.65, a very large f value, which exceeded 5.32. So there's pretty good evidence there that this line is significant. And then the p-value associated with it is less than 1%, which then also supports the argument that the regression is a good fit. All right? So hopefully you have a chance to watch these videos before tomorrow and before our class. And see you there. Take care. Bye-bye.